So today we're going to start taking a look at some of the graphs of an exponential function. So if you remember, our exponential form from yesterday was a times b to the x, where our initial value is a, and a couple things. A can't be equal to 0, right? Because then we'd have 0. And our b, our ratio, is greater than 0. Like that's like our parent graph here. Now, why does b have to be greater than 0? Well, if b was negative, so for example, if we had 2, let's do a different one here. If we had 3 times negative 2 to the x, right? If I was to make a table here, when x equals 1, 3 times negative 2 is negative 6. But when x equals 2, what's negative 2 squared is 4, times 3 is 12. When x equals 3, that's negative 2 cubed is negative 8 times 3 is negative 24. It's bouncing back and forth between negatives and positives. Now, you guys probably remember from last year, exponential growth. When a is greater than 0 and b is greater than 1, it's growing. And why? We're multiplying by a number. But if it's a decay, if our b value is in between 0 and 1, you know, like 0.5. Because again, we start with our value, our initial value of 1, and then we'd be going like by half each time, so it's going to get smaller. So when we take a look at this, is this first one exponential growth or decay, and why? Well, 0.6, so that's going to be decay. And our reasoning why? Well, a is greater than 0, and our b value is in between 0 and 1. Well, how about our next one? Well, 7 over 5 is growth. So our reasoning, well, we know a is greater than 0, and our b value is greater than 1, so it's growth. Our next one is 1/6, so that's another decay. A is greater than 0, and our b value is in between 0 and 1. And then our ratio here is 1.3, so that's growth. And y, again, our a value is greater than 0, and our b value is also greater than 1. And so we're going to get into it. Well, what happens with a is less than 1? We're going to be taking a look at that today. Now, just a reminder what this really means. So if we have the function 3 times 2 to x, again, 3 is our initial value. Our ratio is 2. So when it's 5, what does that actually mean? Well, that actually means, according to exponents, 1, 2, 3, 4, 5. We multiply by 2 5 times. So if we were to go back and try and write these equations for this next one, what would be our initial value? Well, 1.5, and we multiply by 4 to the x power, and our x here is actually 3. Where our next one, our initial value is 3.2. We multiply by 0.8x time, and x just happens to be 2 on this one. All right, so let's think about what these look like here. So if our initial value is greater than 0, so we know our initial value is here, and b is greater than 0. So like if b is 2, we're multiplying by 2, so our next one would be at a height of 4. So this one is our growth. But what about this next one? A is greater than 0, so maybe we still have initial value of 2. But what if b is in between there? For example, what if b is 0.5? Well, it's going to be getting half that height, so it's exponential decay. But now what happens to the other one if a is less than 0? So what if it's negative 2? But again, our b value is greater than 1, you know? So it's kind of like saying if we had 0 and negative 2 was our initial value, what would 1 be? Well, we're multiplying by 2. B is greater than 2, so it's going to go down to negative 4. You could also think about, so it's going to be going down. You could also think about that when it's negative, it's that reflection because a is negative. So again, a is less than 1, so our initial value is low. But what happens, you know, if b is in between there? So again, it's 0.5. Well, our initial value here is negative 2. And if we're multiplying by 0.5, that's our common ratio. That would be negative 1. So it's going to be looking this way. So again, it's that flip. It's a decay equation, but it's flipped. So a couple characteristics here. You're always increasing or decreasing. So if we look back up here, we could say this one's increasing, right? The function is increasing. This one's decreasing. This one's decreasing. And this last one is a increase. There's no extrema, so there's no max or min. It's always concave up or down. So this one's increasing, and it's concave up. Let's see, this one would be concave down. Let's see, that's part of a smile, so concave up. And this one is concave down. And now we're going to talk about limits. And you have possibilities for limit. It either shoots up to infinity, it goes down, or it's going to go to 0. So let's see if we were to write the limit one for this top one. So the limit of f of x as x goes to negative infinity. So as we go backwards on our x's, what happens to our y value? Well, it's getting closer to 0. But what is our limit of f of x as x goes to infinity? So as x gets bigger, our y value also gets bigger. So let's take a look at a couple of these, and we'll see, could we graph this? So example, if this one, what's our initial value? 1, 2, 3, 4, 5. And I'm multiplying by 0.9, so I know it's going to be going down. So it's decreasing. It's going to be concave up. And as our limit as x goes to negative infinity, well, as we go backwards, it shoots up, so that's negative infinity. And as it gets bigger, it's going towards 0. And then this next one, well, what's our initial value? 1, 2, 3, 4, 5, 6. And I'm multiplying by 2. So negative 6 times 2 is going to be negative 12. So it's going down on this side and then going up. So this one is decreasing. It's concave, part of a frown, concave down. And as we go backwards, negative x's, it gets closer to 0. Bigger x's, it's going towards infinity, negative infinity. Now, a couple things about additive transformations. So if you have g of x, and if it's f of x plus 6, so if maybe we add 2 times 3 to the x plus 6. What do you think that plus 6 does? Well, it moves it up 6, right? Now, and a couple things. If the output values of g are proportional, then automatically f has to be proportional and exponential as well.